The second topic in this first chapter is logical connectives. This is pretty much another set of symbols that we will use to do mathematics, by which I mean construct sentences. So we will talk about 5 different logical connectives, which will be negation, conjunction, disjunction, implication, and biconditional. So let me talk about them in greater detail. Negation is just negation. It negates whatever statement that follows it. Logical negation. Conjunction is short for and, so it conjuncts 2 statements by placing the word and between them. Logical conjunction. Simply and. Logical disjunction. That means or. Implication. Logical implication, which simply means implies. And biconditional. That symbol means if and only if. Many theorems have this statement, if and only if. If and only if. So one statement holds when the other does, and vice versa. When and only when. The other statement holds. We will also say in this case that the statements are equivalent. Statements are equivalent. So again, negation, conjunction, disjunction, implication, and biconditional. One of the common ways to introduce these ideas is to use what's known as truth tables. So let's say we have 2 statements, P and Q. P and Q are 2 statements. Meaning what? Meaning they can only take 2 values, true or false. Values true which we will denote by capital T, or false, which we will denote by capital F. Now let's say we concentrate on logical negation first. So how do we properly introduce logical negation using a truth table? Well, whenever statement P is true, its negation negative, P must be false. And vice versa. Whenever P is false, its negation not P must be true. Okay, that's the truth table for the logical negation. Now, the truth table for logical conjunction. Negation only takes one argument, but conjunction takes two arguments. Alright, let's say the other statement is Q. So, what are the possible situations here? P is true, Q is true. P is true, Q is false. P is false, Q is true. And both are false. Right, now, what about the value of P and Q? Well, this is a pretty simple matter. Logical conjunction returns truth if and only if both arguments are true. So it's only when both P and Q are true that P and Q will be true. In all other situations, the returned value will be false. Right, so again, P and Q is true if and only if both P and Q are true. Alright, now how about logical disjunction? Right, that's the OR statement. Let me copy this onto the next page. So the OR statement is kind of dual to the AND statement. The OR statement is false only when both arguments are false. And it's true in all other situations. It's true in all other situations. Right? P or Q is false if and only if both P and Q are false. In all other situations, P or Q is true. Now, the truth table for the implication. That's an interesting one. The thing to remember here is that when we write P implies Q, right, when we write P implies Q in this context, P is called premise and Q is called implication or consequence. So the thing to remember here is that anything based on a false premise is automatically true. So when we write P implies Q, whenever P is false, right, P, the premise, is false, no matter what Q is, P implies Q will be true. When both are true, P implies Q is also true. And the only situation when P implies Q is false is when P is true and F is false. Again, it's important to remember that anything based on a false statement, on a false premise, is true. And you can also say that the implication P implies Q is false if and only if P is true, the premise is true, and the consequence is false. You can now easily construct, as an exercise, the truth table for the biconditional. Biconditional is simply P implies Q and Q implies P. And we will introduce this symbol here, logically equivalent. What this means is the left-hand side takes the truth value precisely when the right-hand side takes the truth value. So they're equal as logical statements. If the left-hand side is true, so is the right-hand side, and vice versa. If the left-hand side is false, so is the right-hand side, and vice versa. So we can easily construct the truth table for the biconditional. Alright, truth, 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 false, false, truth, and false, false. Right, and this time we need biconditional. It's actually a very simple matter because P and Q are P occurs if and only if Q occurs. Simply means that they both have to take the same value, either both true or both false. Right? In the other two situations, that will be false, because, for instance, Q will imply, in this case, Q will imply P, but P won't imply Q. Same here. In this case, when P is false and Q is true, P will imply Q, but Q won't imply P. So these statements will be false. So that is the truth table for the bicondition. So now I'd like to mention a few important properties that these symbols abide, or that these symbols have. The first of them is the so-called De Morgan's laws. Let's make it a theorem, De Morgan's laws. These are two statements. One of them that the negation of the AND statement is the OR statement of negations. By the way, the parentheses here tell you the order of operations. The parentheses tell you that you first apply the AND statement, and then to the result of the AND statement you apply the negation. And vice versa, the negation of the OR statement is the AND statement of negations. Note the duality, right? When you negate the AND statement, you get the OR statement. And when you negate the OR statement, you get the AND statement. It's a nice homework exercise to prove this theorem using the truth tables. You would have to construct a truth table. It'll have 4 rows, just like the tables on the previous page. And you would have to compute the value for the left-hand side for all possible P and Q, and the same for the right-hand side. And see that the two columns, the one for the left-hand side and the one for the right-hand side, are identically equal. Another important property here the law of contrapositive. The law of contrapositive. This one says that P implies Q is logically equivalent to not Q implying not P. Let me check this one. It's really, really easy. Right, so to prove this, all I need to do is construct the truth table. Right, P implies Q, not P, not Q, and not Q implying not P. Right, again, P implies Q is true unless the premise is true and the consequence is false. So not P gives me the column false, false, truth, truth, and not Q gives me the column false, truth, false, truth. Now, when does not Q imply not P? Right? When both are false, this is true. Right? When the premise not Q is true and the consequence is false, that's false. When the premise not Q is false, that's true. And when both are true, that's also true. Now you compare the two columns. They are identically equal. That finishes the proof that the two statements are logically equivalent. Again, meaning that they take the same value for the same values of the statements P and Q. Alright, another useful statement is the negation of implication. Negation of implication. This one says that when you have an implication and you want to negate it, that's equivalent to the statement P and not Q. Right, we can actually give a nice example to this statement to clarify its use, to give an example of its usage. Right, say let the statement P be that it rains. And say the statement Q be I will stay home. Right, so then P implying Q would read as, if it rains, I will stay home. I'm staying home. If it rains, I'm staying, or rather not home, I'm staying inside. If it rains, I'm staying inside. Now, how would the negation of P implies Q look like in this case? Negation to P implies Q. Right? According to this theorem, it's P and not Q. Well, P is, it rains, and I'm going out. Not Q, right? Q is I'll stay inside, so not Q means I'm going out. I'm going outside. So negation to P implies Q is it rains and I'm going outside. All right, as far as the proof goes, you can write down the proof exactly the same way as we did for the law of the contrapositive. Right, you would construct the negation the truth table, and verify that the left-hand side and the right-hand side take on the same values for all possible combinations of values of P and Q. And otherwise you will have columns for the left-hand side and the right-hand side identical, as we did in this proof. Alright, the next theorem that we will commonly use, or frequently use, is called the distribution laws. This time we have three statements, P, Q, and R. And say you consider the conjunction of Q and R, and then you disjunct this with statement P. So P or the end statement of Q and R. That actually is logically equivalent to, you can kind of distribute P and Q, P over Q and R, as if this was multiplication, this was addition. Right? So it will be P or Q and P or R. And the same with the reversed symbols, right? When you have Q and R, and then take the conjunction of this with P, that's logically equivalent to, again, view this as multiplication, and this as addition, right? It will be P times Q, or P and Q, plus or P and R. You can easily verify this again using the truth tables. Let me maybe verify one of them. Right, this time the truth table will have 8 rows. Right, because there are now 3 statements, P, Q, and R, and each one of them can take 2 values. So 2 to the power 3 will be 8 rows. Right, now let's make a column for Q and R. Column for Q and R. Right, so both, okay. So remember, Q and R is true if and only if both Q and R are true. Right, and it's false in all other situations. Now let's make a column for P and Q or R. P or Q and R, sorry, I misread. P or Q and R. Alright, this time we consider the OR statement of P and Q and R. The OR statement is true if and only if at least one of the arguments is true. So we have keys here, right? T here and F's here. That is the left-hand side. Now let's consider the right-hand side. For the right-hand side, let's write down statements P or Q and P and R. Again, P or Q is true if and only if at least one of P and Q is true. So we have T's here, and whenever Q is true, and F's here. P or R is true if and only if at least one of P or R is true. And now we consider the AND statement of the last two columns. P or Q and P or R. Again, the AND statement is true if and only if both arguments are true. So we have true in the first four lines, false here, false here, false here, and false here. Now we compare the two columns, the column for the left-hand side and the column for the right-hand side. And we see that they're not quite, they're not identically equal, so there's a mistake somewhere. There's a problem here. All right, let's check this particular line. So Q and R returns true in this case. P or Q and R returns true. P or Q returns true. P or R also returns true. And then the AND statement of true and true should also return true. That was a mistake on my part, so this should be true. Slip of the pen, so to speak. Now we see that the two columns are identically equal. So that establishes the validity of property 1. You can do the same work to prove statement 2. These are used very, very frequently. Alright, now a small remark about the order of operations. I kind of already said that we use parentheses to emphasize the order of operations here. So parentheses here tell you that you first consider the AND statement, the conjunction of Q and R, and then the result is considered in disjunction with P. Without parentheses, this statement becomes ambiguous, and the result of a logical statement actually depends on the order of operations. And just like in algebra, where we agree to do multiplication first and then addition, we make a convention about the order of operations of logical connectives. of logical connectives. The order of priorities is the following. First negation, then disjunction, then conjunction, then conditional or implication, then bicondition. Right, so parentheses were absolutely important here because, as you see, without parentheses, if we had the statement P, O, Q, and R without parentheses, right, that actually means P or Q in parentheses and then and R, which is not what we had in that theorem. So parentheses were important because we want this, not this. These are different things. These are not logically equivalent statements. Right? It's not the same. As P or in parentheses Q and R. You can construct the truth tables for this statement and see that they're not logically equivalent. Logical connectives in general make your life a lot easier because you can keep track of logic when solving problems, and I'll show you a number of examples. Here's one maybe very simple example. Demonstrating the idea behind logical connectives. So we have the quadratic equation x squared minus 3x plus 2 equals 0. We agree for now that unless otherwise stated, all our symbols represent real numbers. You can easily see that the roots of this equation are 1 and 2, and so that means that x squared minus 3x plus 2 is 0 if and only if either x is 1 or x is 2. To be safe, I would put another round of parentheses, another set of parentheses. Not a very interesting example, but it will be useful to see how connectives are used in mathematical reasoning. Now, a much more involved example. Logic behind solving equations and inequalities with radicals. Equations and inequalities with radicals. We will have 5 types. Say you have an equation like this. Square root of some expression containing x equals some other expression containing x. Right? A common mistake would be just to take and, right, this is an equation in x. A very common mistake that many students make is just to take and square up both sides and then say that f equals g squared of x. The problem here, why this is a mistake, is that there might be some values of x making this true. such that for those values of x, g is negative, making this impossible. So definitely the fact that root f equals g implies that f equals g squared. But the converse is usually false. For example, you can clearly see that 1 equals negative 1 squared. Right? And say this is my f squared, and this is my g. G is negative 1. Can you really say from here that f, which is 1, equal root f, which is 1? This, I mean, was f. Root f, which is 1, equals g, which is negative 1. This certainly is false. Right? So this implies this, but not vice versa. So you can't just raise both sides to the second power and claim that this equation will be equivalent. Right? You might get some extraneous solutions. So the right way to go is to ensure that you can always get back. Right? The reason why you weren't able to get back from the right-hand side to the left-hand side was that even though f clearly must be non-negative, because f equals g squared, and g squared must be non-negative, when taking square roots from here, right, you don't get g back, because square root of g squared is not in general g, right? It's not necessarily g, it's either g or negative g. So it's absolute value of g, which is not quite the same as this. So to be able to get rid of the absolute value here, you must assume that g is non-negative. Right? So under the assumption that g is non-negative, the two things become logically equivalent. Remember, the braces here, the left brace here means the end statement. Again, simply raising both sides of this equation to the second power is a mistake. You might get solutions of this equation that are not solutions of that equation. When solving equations or inequalities, always make sure all your steps are biconditionals. Say, for example, you are solving the inequality root f is greater or equal than g. What would this be equivalent to? Well, that depends whether the right-hand side g is positive or negative. Right? If say g is negative, the inequality will be true whenever the left-hand side exists. The left-hand side exists when the expression under the radical, which is f, is non-negative. Or when the right-hand side g is non-negative. I can safely raise both sides of the inequality to the second power. right? And these two systems are in disjunction. So either that or that. I can put the bracket symbol. Remember, bracket in this context means or, disjunction. Once again, we have this inequality. If the left-hand side is negative, if the right-hand side is negative, if G is negative, the inequality will be true whenever the left-hand side exists, which happens exactly when the expression under the square root, which is f, is non-negative. Otherwise, if the right-hand side G is non-negative, I can safely raise both sides of the inequality to the second power. And I could go back from this, right? If I were to take square roots, under the assumption that G is positive or non-negative, I could get rid of this, of the absolute value, and get back the same inequality. Maybe a few more. Of course, if you are solving that inequality in the strict sense, root f is greater than g of x, right? You just need to amend the inequalities on the right accordingly, right? If g is negative, it's enough for f to exist. But if g is positive, I can safely raise both sides of the inequality to the second power. Alright, and a similar reasoning when the inequality is less or lesser equal. Say when you have root f less than g, again you must assume that if you simply write that f is less or equal than g squared of x, I believe in one direction that's true. But how about the opposite direction? Can you go the opposite direction? Not really clear. Because, for instance, this inequality may be true when f is negative, right? There may be some x for which f is negative, and this is positive, and this inequality will be true, but taking square root won't be an option, because f is negative. So you must necessarily assume that both f and g are non-negative. The non-negativity of g, again, is needed to get rid of the absolute value when you take the square root of g squared, right? Because g is non-negative, absolute value of g equals g. And the same when, well, a very similar reasoning when the inequality is non-strict. Right, we simply raise the inequality to the second power under the assumption that both sides are non-negative and exist. So here is a much more interesting example demonstrating how we use connectives to solve equations and inequalities. So the inequality is this. Solve the inequality. X squared minus 1 over square root of 13 minus x squared greater or equal than x minus 1. I will first show you a bogus solution that unfortunately many students would submit. It's a very, very common mistake. Well, the solution goes like this. We factor out x squared minus 1 on the right, on the left, to write x minus 1, x plus 1. And cancel out by x minus 1 on each side. That would give me x plus 1 over root 13 minus x squared greater or equal than 1. Then I would multiply by the square root both sides, x plus 1 greater or equal than root 13 minus x squared, which I can of course write as root 13 minus x squared less or equal than x plus 1, which is an inequality of this type. And then I can follow this scheme. Right, so I would raise both sides of the inequality to the second power, ensuring of course that both of them exist and are non-negative. Right, so this gives me x greater or equal than negative 1. This gives me x squared minus less or equal than 13, which means x is between negative root 13 and root 13. And this here requires a little bit of algebra. So 13 minus x squared less or equal than x squared plus 2x plus 1. So we have 2x squared plus 2x minus 12 is greater or equal than 0, and I can cancel by 2. When I cancel by 2, I get x squared plus x minus 6 greater or equal than 0. The roots of the quadratic are negative 3 and 2. So we have a parabola opening upward with roots negative 3 and 2, and it's greater or equal than 0 to the left of negative 3 or to the right of 2. Right, and combining these three situations, what do we get? Well, x cannot be less or equal to negative 3, because it has to be greater or equal to negative 1. So we must therefore have x greater or equal than 2, x greater or equal to negative 1, which is automatically true, and x between negative root 13 and root 13. So that gives me that x is between 2 and root 13, including 2. As you will see in a minute, this is the wrong answer. So what was the mistake? The mistake, of course, occurred when I did the division. This is because I divided by x minus 1 without checking whether x minus 1 was positive. Remember, when you divide an inequality by a negative expression, the sign of the inequality flips. I didn't flip the sign, but I never checked if my dividing by x minus 1 was actually permissible. This is a very common mistake. So never divide, never cancel an inequalities without checking first whether by what you're canceling is positive or negative. So here is now the correct solution. So remember the inequality was x squared minus 1 over root 13 minus x squared is greater or equal than x minus 1. I strongly recommend that you keep all your algebra in a chain of biconditionals. Right? When you do that, whatever you get for x will be the final answer. It won't be just the answer to the previous inequality. It will be the answer to the original inequality too. All you have to do is just really think whether all your steps are biconditionals, whether this implies this, and vice versa. What you get implies what you began with. So the first step in my solution will be factoring out x minus 1. And maybe I can move x minus 1 from the right hand side to the left. Now let's factor out x minus 1. So what's left in parentheses is x plus 1 over square root minus 1. Or we can find the common denominator. Now, we have a product of two things, non-negative. When is the product of two things non-negative? Product of two things is non-negative if and only if either both are non-negative or both are non-positive. Product is greater or equal than 0 if and only if either both factors are greater or equal than 0 or less or equal than 0. So our last step is equivalent to the disjunction that either x minus 1 is greater or equal than 0, and then the other factor is greater or equal than 0. Or x minus 1 is less or equal than 0, and then the other factor is less or equal than 0. Alright, now we solve each system separately. Right? What can we say about this fraction? When is the fraction non-negative? Right? A fraction is non-negative let's say a over b. A fraction a over b is non-negative if and only if what? Either the numerator is non-negative, but then the denominator is strictly positive, or the numerator is less or equal than 0, but then the denominator is strictly less than 0. So we're going to use this fact in our situation. Alright, so for the first system we have x minus 1 is greater or equal than 0. But this actually is an easy situation, because in this fraction we have a square root, and the square root cannot be negative, so this situation is impossible for us. So we must have this strictly positive to ensure we're not dividing by 0. And this is greater or equal than 0. Or in the other system, again, the numerator is non-positive, and the denominator is strictly positive. Okay, so what do we do with this? So let me maybe do some simple algebra first. So this x minus 1 greater or equal than 0 implies x is greater or equal than 1. Right? This now implies that x is in between root 13 and negative root 13. And here I can write this like this. Or I can actually square immediately. I can square this immediately. That's what the first system gives me. Now the second system is slightly more complicated. So again I have x less or equal than 1. And well, 13 minus x squared is greater than 0. But when I solve this inequality, I have to consider different situations, right? Because I could write this as x plus 1, or rather root 13 minus x squared greater or equal than x plus 1. Well, if x plus 1 is less than 0, right, it's enough to have the left-hand side exist, which is automatically true actually because of the because we already have that condition. On the other hand, when x plus 1 is greater or equal than 0, we can square. So don't get too discouraged by how complicated the system is. It's not actually that much complicated. Let me copy this to the next page. So for the first system, we have we already worked with that quadratic inequality, right? When we wrote our round solution, right? And we know roots are 2 and negative 3, and the inequality is in that direction. So I can have this as x greater or equal than 1, x between root 13 and negative root 13, and otherwise x is either less or equal than negative 3 or greater or equal than 2. That's what this system gives me. Now, what does this system give me? Well, if we work step by step, we have x less or equal than 1. We have x between root 13 and negative root 13. And we have here, when we work with this, we have that either x is less than negative 1 and between root 13 and negative root 13. Or that x is greater or equal than 1. And when you solve this inequality, right, x must be between the roots of the quadratic trinomial, between negative 3 and 2. All right, and that's either or. So what does that give me? Well, the first system, right, it's easy if you draw these points on the real line. So x cannot be less than negative 3 because it has to be greater or equal than 1. So I can forget about that condition. Then it must be greater or equal than 2. It must be greater or equal than 2. Which is stronger than greater or equal than 1. Right? And it must be less than root 13. So the first system simply gives me that x is greater or equal than 2 and strictly less than root 13. Now what about the second system? Well, in the second system, this system cannot have a solution because it's inconsistent with the condition that this one is inconsistent with the requirement that x be less or equal than 1, except if x is 1. So what do we get here? We can definitely simplify it. This condition may be dropped because it's automatically included here anyway. Now, what about this? Right, so this means, so what do we have here? We have let's say this system. We have this system, right? So x is less than 1, less than negative, x is less than negative 1. I might have made a mistake in the previous step. Yes, I think I did. So this must be here, x is greater or equal than negative 1. Okay. So this system gives me that x is between negative 1 and 2. Or that x is less than negative 1. Either that or that, right? Well, when you unite them, that simply means that x is less or equal than 2. And when you consider x is less or equal than 1, x is between negative root 13 and root 13, and x is less or equal than 2, we see that when we draw these points on the real line, 2, 1, and root 13, which is greater than 3, so it's greater than 2, negative root 13, we see that the solution is between negative root 13 and 1. And by the way, it's not conjunction, it's disjunction, so it should be or. So x is between negative root 13 and 1. So that means x is in negative root 13 and 1, including 1, or x is in 2 root 13. Now, if you compare this to the answer that we got when we did our own solution, right, we lost half the answer because we did have from 2 to root 13, but we didn't have from negative root 13 to 1. Right? Because we divided by a possibly negative expression and didn't flip the sign of the inequality, we didn't get the right answer. And there were, as we know now, x's for which x minus 1 is negative, for which the inequality is true. So by canceling by x minus 1, we lost all those x's. That is a nice example showing the importance of biconditionals. Whenever you solve an algebraic equation or inequality, always make sure that all your steps are biconditionals. That you can get from here to the previous step, from previous step to the second to last step, and so on. Right? You can get from the original inequality to the very last step, which implies the answer, and vice versa.